GPT-4 reportedly has 1.8 trillion tiny dials inside it, and not one was set by a human hand. Engineers don't write the rules. They show the machine millions of examples, and it turns its own dials, trillions of them, until its guesses stop being wrong. That's the whole secret. In the next few minutes I'll show you exactly how that works, what a neuron, a weight, and training really are, and by the end you'll understand AI better than most people who talk about it for a living. First, untangle the three words people use interchangeably. Think of three circles, one inside the other. The biggest is artificial intelligence, any technique that makes a machine seem smart, going back to the 1950s. That includes old systems with handwritten rules that never learn anything. Inside it sits machine learning, systems that learn patterns from data instead of being told the rules. And inside that sits deep learning, machine learning that uses deep neural networks, the engine behind ChatGPT, Gemini, and image generators. Simple rule, all deep learning is machine learning, all machine learning is AI, but not all AI actually learns. Start with the building block. A neural network neuron isn't biology, it's a tiny piece of math. It takes a few numbers in, multiplies each by a weight, adds them up with a bias, and runs the total through a function that decides how strongly it fires. That's the entire neuron, a weighted sum and a squish. A weight is just one number, the strength of one connection. Stack these neurons into layers, input, hidden, output, and a single frontier model holds over 1 trillion of them. Here's the key idea, those weights are what the model knows. The whole network is one giant tunable equation, and training is nothing more than finding good values for every dial. So how do those weights get set? There are three classic ways a machine learns. Supervised learning is the most common, you give it labeled examples, 10,000 photos each tagged cat or dog, and it learns the mapping from input to answer. It's a teacher with an answer key. Unsupervised learning gets no labels at all, it hunts for hidden structure on its own, grouping similar customers, spotting anomalies. And reinforcement learning has no fixed data set, an agent acts, gets a reward or penalty, and learns by trial and error. That's how DeepMind's AlphaGo beat the world champion in 2016. Chatbots add a twist called self-supervised learning. The model hides the next word and tries to predict it, making its own labels out of the entire internet. Here's the heart of it, the one loop that is all of training. Step 1, feed in an example and let the network guess. Step 2, compare the guess to the right answer and compute the error, a single number called the loss. Step 3, backpropagation, using calculus, work backwards through the network to figure out how much each individual weight contributed to that error. Step 4, gradient descent, nudge every weight a tiny step in the direction that makes the error smaller, like rolling a ball downhill toward the lowest point. Then repeat, with millions of examples, again and again. That's it. Guess, measure how wrong, adjust every dial a little, repeat 1 trillion times. Nobody wrote the rules, they emerge in the weights. That loop trains a specific kind of network. Today's language models all run on an architecture called the transformer, introduced by Google in 2017 in a paper titled Attention is All You Need. Its trick is self-attention. Instead of reading word by word, it weighs how much every word relates to every other word, all at once, in parallel. That's what lets it hold context across long passages and train fast on GPUs. And that's literally the T in GPT, generative pre-trained transformer. So when you hear LLM, picture this, a giant neural network, trained by that loop, using attention to understand how words connect. Zoom out and the whole pipeline has 3 stages. First, data, collect and clean an enormous dataset, and quality matters as much as size. Second, training, run that loop on big GPU clusters for days or months. The output is a single frozen file of weights, that file is the model. Third, inference, take the trained weights and answer a brand new prompt in milliseconds. Here's the part most people miss, training is the factory, hugely expensive, but you pay it roughly once. Inference is the product, cheap per answer, but multiplied by billions of queries, it's where the real running cost lies. Train once, infer forever. Now the scale, because the numbers are genuinely staggering. Parameters are the weights, the dials. GPT-2 in 2019 had 1.5 billion. GPT-3 jumped to 175 billion. GPT-4 is reportedly around 1.8 trillion, though OpenAI never confirmed that, so treat it as an estimate. Meta's Llama 3.1, which is fully open, has 405 billion. On data, GPT-3 trained on about 300 billion tokens. A token is roughly 3/4 of a word, while Llama 3.1 read over 15 trillion. And the compute, Llama's biggest model took 39.3 million GPU hours on more than 16,000 H100 chips. One single GPU running that alone would take about 4,500 years. Put that same ladder on one chart and the real story jumps out. It's not a story about a clever new idea, it's a story about size. In barely 4 years the biggest models grew roughly 1,000-fold in parameters, and the field kept finding the same thing: make it bigger, feed it more, and it gets better. By now, more than 30 models from a dozen different labs have been trained at GPT-4 scale or beyond. That's the single biggest reason AI suddenly felt like it woke up, not a breakthrough in theory, but the very same loop run far, far bigger. Scale, it turned out, was the feature. None of this appeared overnight. Back in 1958, Frank Rosenblatt built the perceptron, the first trainable artificial neuron. In 1986, Geoffrey Hinton and colleagues popularized backpropagation, the trick that finally let deep networks learn. Then in 2012, a network called AlexNet crushed an image recognition contest by running on GPUs. That's the spark that lit the whole deep learning boom. In 2016, AlphaGo beat the world Go champion, reinforcement learning's landmark. And in 2017, the transformer arrived, the architecture behind every chatbot you use today. 60 years of slow build-up, then a sudden explosion. This isn't a lab toy, the same loop is already running your day, mostly invisibly. Roughly 70% of everything watched on YouTube, and about 80% of hours streamed on Netflix, come from machine learning recommendations, not from you searching. Behind the scenes, models score card transactions for fraud in milliseconds, and triage medical scans, flagging diabetic eye disease, reading mammograms, often at expert level. Your phone runs speech-to-text and live translation on device. Waymo's cars now give over 500,000 paid robotaxi rides every week on neural net perception alone. And DeepMind's AlphaFold predicted the shape of more than 200 million proteins, nearly every one known, work that won the 2024 Nobel Prize in Chemistry. The chatbot is just the part you can see, so why should you care how the gears turn? Because that makes AI infrastructure, not a gadget, and understanding the mechanism is a built-in BS detector. Once you know it's pattern matching from data, not a mind, not magic, 3 things follow. It can be confidently wrong, because it predicts what's plausible, not what's true. It inherits whatever bias lives in its training data. And it's only ever as good, as fair, and as current as the examples it was shown. Garbage in, garbage out isn't a slogan here, it's literally how it works. So where does it go from here? The era of just making models bigger is ending. Epic AI projects the supply of high-quality human-written text could be effectively used up sometime between 2026 and 2032, so the field is pivoting 2 ways. First, to efficiency, small, specialized models that run right on your phone, where a tuned 7 billion parameter model can beat a giant one on a narrow job. Second, to reasoning and agents. Instead of answering in one shot, models now think step by step and chain tools to get work done. As for AGI, a machine that matches humans at almost everything, leading labs say years away, honest skeptics say we don't even have a reliable test for it. But the real choke point isn't ideas anymore, it's energy. Global data center electricity is on track to roughly double to about 945 terawatt-hours by 2030, near 3% of all the world's power, says the IEA. Whoever has the data, the chips, and the megawatts owns the frontier. Here's the sticky idea to walk away with. The algorithms behind all of this, backpropagation, gradient descent, the transformer, are completely public. They're taught in undergraduate courses, you could read the original papers tonight. So the real advantage in AI is not the math. It's the scarce inputs that almost nobody has, mountains of clean, proprietary data, tens of thousands of GPUs, and the megawatts to run them. Whoever controls data, chips, and power controls the frontier. The recipe is free. The ingredients are the whole game.
If you remember one thing, remember this. An AI never learns rules the way a person does. It does one humble thing at unimaginable scale: it guesses, it measures how wrong it was, and it nudges billions of dials a tiny bit closer to right, over and over, 1,000,000,000,000 times. That's not magic. That's not a mind. It's relentless, brute force error correction. And once you see it that way, the whole field stops being mysterious.
And that's how AI really learns: nested ideas, machine learning, deep learning, built from neurons that are just math, trained by one loop that guesses and corrects, scaled up to trillions of dials, and now bounded by data, chips, and power. Next, we take this exact same idea, guess, measure, correct, and watch it learn to paint pictures from pure noise. If you want technology explained with the hype stripped out and the mechanism left in, subscribe to Technologia today. We don't just tell you what's new, we show you how it actually works.